So welcome to this lecture on advanced digital system design. In the course digital system design with PLDs and FPGAs. In the last lecture we have looked at how to reduce output delay in finite state machine. There were two techniques basically to decode the output from the next state instead of the present state. The second technique was to encode the output in the present state. Okay. So quickly before getting into today's portion we will run through those slides quickly. So let us look at this. So basically our aim was to reduce the output delay, and so these are the two techniques we said: output decoding from the next state. So in the normal course of time we decode the present state to generate the output. Our idea is that hopefully there is a if you put the output logic here and followed with a set of flip flops, so that when the clock comes you get the output along with the present state. So the only output delay is TCQ, that's the idea. So that is how we have put it. From the next state logic you have output logic and the output flip flops. Now there are two paths, two register to register, two different kind of paths. There are many paths. Maybe if there are 3 flip flops 3 into 3 9, if there are 2 outputs then 3 into 2 6 paths in this side. But here at least by the number of terms this particular path has more terms: TCQ, T next state logic, T output logic and the setup time. Okay. Earlier one advantage is that this is coming kind of one after the other, so it could be optimized. Earlier if you look at the earlier diagram, this output logic was after the register boundary, so there is no way it can be combined with this, so there was no kind of optimization possible there. But it may happen that this two put together can become as equal to the earlier one. Then we have an advantage because everything is same, the clock cycle is same, clock cycle is not affected, and the output delay is reduced. So that's the advantage of this scheme. And the other scheme is to use the present state as output. Definitely there are lot of points to kind of ponder because how many number of outputs are there, how many number of state flip flops are there, what is there, one could be greater than the other one and things like that. But at least we have seen that when the number of outputs are like equal to the number of flip flops, and if the pattern is unique for each state, straight away we can use one of the flip flop as for one output and the other one for the second output. There is no harm. But if there is any kind of repetition, like in this case S1 and S3 has the same output pattern. Okay. So in that case we will be forced to add an extra bit. That means the state present state the state flip flops will be 3 flip flops though we have only 4 states. This is to decode the output from the state because there are repetition as far as the output pattern is concerned in this case. So we add extra bit to kind of demarcate them, and but still we end up having, at the cost of one flip flop, our output delay is reduced. And we have seen another example, much more a complex example, where one output pattern is repeated twice and one 3 times. Then we are forced to add 2 extra bits to make a difference, like 0 0 0 1 1 0. And as I said, there are 5 state flip flops or the present state flip flop, but that account for like 2 raised to 5 32 pattern, but we have only 4 output there are only 2 raised to 4 possibilities, but because the output is repeating in state we are forced to add this 2 extra bit. So the rule is that you identify the state with same output values. From these identify the state where one output pattern repeat maximum and additional bit to make the output pattern distinct. You don't have to worry about whether something is greater than or less than. If you try this algorithm, this will work out, and it's a good thing to try. It's a really good thing to try. The tools may not do it, because that we have already seen that the various attributes, the tools normally allow the sequential kind of encoding, the gray coding, or the 101 and things like that. 101 as a possibility of this happening, or because output can be delay can be reduced. We will see that later when we look at the FPGA. So that is what we have seen in the last lecture. Today we are going to look at a serious issue called synchronization, okay, and that is related to an issue in a flip flop called metastability. Basically it is not it's an issue inherent in a cross couple latch, okay. Since we build flip flop out of a cross couple latch, the same problem comes in the flip flop, and we build data path and the finite state machine using flip flops. So we are again have the same problem. So it all start with the latch, but we don't have time to look at from the transistor level or at the inverter level down to here, okay. Actually normally if you learn that way you can get a good grip on it, but we will abstract it as far as the flip flop is concerned. What is the rule to follow, and I will tell a gist of it, why it is happening and how to handle it. That should equip you to handle most of the situation you come across. We are not again discussing all possible advanced technique to do the synchronization, which I hope you can follow it up with the basic. And this course we are already it contains quite a lot of things. Now to add this is maybe little too much of a scope. So let us look at the problem of metastability in the flip flop. So we have already learned that in an edge triggered flip flop, say you have a clock D and Q. Normally a behavioral kind of description is that when the clock edge comes, whatever is at the D is propagated to Q with a delay. But we know that for that to happen properly, okay, the data here has to arrive sometime before the active clock edge, that in this case the positive edge, and that time is called setup time or TS. Not only that, the data after the clock edge it has to remain there for some time, that time is called hold time. So unless the data at the input meet the setup and hold time, the Q will not get this copy of this D, copy or the value of D. The D will not be transferred to Q properly, okay. So that is what is, I mean, we have many times we have learned that for successful transfer of operation of the edge triggered flip flop, you have to meet the setup and hold time at the input. Many times it is not discussed what happens if it is not met, okay. So that is what we are going to do today. Now the game is that, so this is the essential behavior of the flip flop. The data should arrive setup time before the clock edge, data should remain kind of hold time after the clock edge, active clock edge, and if so happens from the active clock edge with some delay this output appears, okay. Now that means that though we say in a functional way, many a times when you learn at the beginning you draw kind of the waveform without delay, there whatever the edge, whatever is the value at the edge, it is transferred to the output. That is how it is done at a behavioral level. But there is no magic, there nothing can work like a magic. Just an edge comes, the output cannot instantaneously go there. And you also would have studied a master slave flip flop which is working as an edge triggered flip flop, because most of you would have learned master and slave configuration, and that is a essential logic circuit for edge triggered flip flop. And most textbook give two cross coupled latch one after the other. So during the negative clock period the master is in the transparent mode. When it goes positive the master is cut off and the slave, whatever is captured in the master is transferred to the slave and you get the output. Okay. So there is no magic, there is no like edge trigger magic, as soon as the edge comes, as if something happens during the edge, nothing happens during the edge in digital, that either it is 1 or 0. So something happened to the master latch during the clock period is low, something happened to, and that is cut off, something happened to the slave latch during when it is high, whatever is captured in the master is transferred to the slave. Okay. So that is why this setup and hold time come, and as I said I am not going to have an analysis due to lack of time, but then you can definitely go back and look at the architecture of the master slave. Not only what you have learned, any master slave, there are different master slave architecture, though some things are not called the master slave. You can take the like if you remember the 7-4 TTL series, you can take 7-4D 7-4 flip flop and look at the internal diagram. You will find that there is a kind of master slave architecture which is not same as what you have learned in say in the textbook, and the number of gates used will be less and the propagation delays also will be less in those configuration, but the analysis is same. So what I am saying is that the game in a gist, so that I don't leave some curiosity kind of like if I say accept as it is and you don't know where it is coming from, suddenly a magic. So I just want to tell that when the clock period is low the master latch will be in the transparent mode. Okay. So master latch is capturing the input, but the latest when it can capture is some time before this is getting cut off. Okay. Because when this edge comes and when it turns positive master input is cut off. Okay. So but the master latch to kind of set, there is a cross coupled latch delay. Okay. So that delay before this clock edge is a setup time, and we have learned that there will be, because the master is enabled during the negative, the slave is negative period, the slave is enabled during the positive clock period. So there will be inverters in the clock path. So there will be like the normally you will have the master latch delay minus the inverter delay will be the setup time, because that is the latest a master latch can set before the clock edge happens. Okay. Now the clock edge comes, now because of the inverters and the clock path it takes some time to cut it off, input to cut it off. So during that time nothing should happen to the D, then the master latch will be upset. So upset in the sense the value will be upset. So there is a hold time which is equal to the, you can say the inverter delay in the clock path. So that is a hold time. Now when this clock period is enabled, the slave latch will take some time to set, that is the propagation delay. Okay. So that is how this comes, as I said during the negative clock edge clock period the master is in transparent mode. So before it is cut off what is the latest the master can latch, that is the setup time, that is a cross couple latch delay minus the inverters, any inverters in the path, and when it is cut off, when it goes to positive, that inverter delay has to be kind of met, because then only it will be really cut off, that is the whole time. And then when it is when the slave is enabled, the master output is latched onto the slave. So that latch delay plus any inverter delay in the clock path, if you analyze it you will get that is the propagation delay now. So that is how this comes. That means once again for the D to go to Q you have to meet setup and hold time, that is all. But what happens if this is not met, okay, that means the master is getting cut off and you are still changing the input, okay. So what happens then? What happens is that again that needs a little bit of analysis, which I cannot kind of which we have to go back to the cross couple latch. So since as I said the lack of time, we will just kind of abstract it. What happens is that if the setup or hold time is not met, many things can happen. One thing the best can happen is that, like suppose the output was 0 here and you are trying to drive a 1 upon the clock edge, that means we are expecting this 1 will come here, okay. But if the setup or hold time is not met, then we are not sure, the whatever the 0 at the output may remain there 0, or it might become 1. So we can't say, maybe it will change state or it may not change the state, okay. It is still an acceptable behavior, there is no harm, because earlier it was 0, we are expecting it to go to 1. Since it is the data is coming in this changing in this window, it is not set up, it is not the data is not set up properly. So data is not transferred, still it is okay because it is 0, this is 1, and we are hoping that next clock edge come. So if the data remains, and normally the data does not remain just like that, data will remain for 1 or 2 clock period and the data is transferred properly. So a missed trigger is a very good thing, the best thing you can hope for. If the setup and hold time is violated, the best one can hope is that let it miss trigger, that means instead of going to 1 let it be 0, there is no harm because earlier it was 0, and the next clock edge it becomes 1, okay. Now another effect of this metastability in flip flop, this behavior is called metastability. Another effect of that is that if the data is changing within this window close to the clock edge, it will take the output will either become 0 or become 1, but it will take long time to resolve, like that say output was 0, it was going to 1, but it would not transit fast, it will take some time and settle it to 1, okay. So that is another issue which is already bad, because in a register to register path we say T clock is greater than TCQ plus T com plus T setup, and we have fixed the maximum TCQ. Now if it takes long time to resolve, that will violate the setup time at the destination flip flop, and that can cause metastability there, okay. So it can propagate, this whole game can propagate from one flip flop to the other, it's very bad. The worst case, so two things, either it miss trigger, it takes long time to miss trigger, like even for output to resolve it takes long time. Third effect is that it can get stuck in between the logic levels. Suppose you know that in a 5 volt say the lowest high value is say 3 volt and the highest low value is 2 volt. We will expect always the logic 1 to be greater than 3 volt and logic 0 to be less than 2 volt, but what happens is that in the case of metastability it may happen that such a flip flop can have a output which is 2.5 volt, okay. Now that is very dangerous. If that 2.5 volt goes to a logic circuit, a combination circuit, what can happen is that it can drive the transistors inside to active region. So instead of kind of a switch, it will act as an amplifier. Any noise it will drive to saturation, so it will start switching. Okay. So there could be a lot of errors if it is not kind of in the design, it is not taken care. This metastability can cause a lot of errors. Okay. The mistrigger is very safe because as I said, it may go to 0 or 1, still it is okay, but if it gets stuck in between and that whatever is being driven can also get into metastability. So it is a disastrous thing, and many a times this issue is not taught in the basic course, but it's a very serious thing, you know, and most of the time the design practices a novice use doesn't consider the metastability. It's a really bad thing to do, but most of the time because of the reliability these devices are very fast and the probability of that thing happening is less, we are saved, but this should be kept in mind. So that is the basic issue, what is called metastability. Okay. In an edge triggered flip flop, if the setup or hold time is not met, we are not sure of output, it can take longer to resolve, it can get stuck in between, which is the worst kind of thing. So that is what I have summarized here. If setup hold time is violated, flip flop can sample input wrongly, output could be 1 or 0. That means in the case if it was 0 before, it may remain at previous value or transit to a new value. Output may take a long time to resolve if the input changes close to clock edge. The worst case, output can get stuck in a non-logical value and it can remain there in such a state for indeterminate amount of time. We don't know how long it takes, you know, maybe it will come out of it after 1 second, 1 hour, 2 hour, 1 day, we are not sure. Okay. We cannot say and it's a probabilistic thing, you know, no, we cannot definitely say that this will happen, or if it happens it comes out with certainty. Okay. It's a probability. So that is metastability, but let us come back to the data path and sequential circuit. As I said, we use flip flops and combination circuit. Okay. So all the data paths are built of the flip flops or registers and combination circuit. Similarly the FSM also use the registers, the state registers and the combination circuit, next state logic, output logic and so on. So now this has potential chance of probably there is a chance of flip flop getting into metastability, but when we design we analyze all the register to register path and we choose like at the destination register we always try to meet the setup time by choosing the proper clock period, like we will say T clock is greater than that path delay. That is taken care in the analysis while simulating all that we make sure that the clock period is not exceeded. Similarly at the destination register we also make sure that hold time is not violated. If it is violated we add extra combinational delay and sort it out, you know. So we take care of these both condition, and if there is a skew of the clock, which we have not I think formally learned in this course, which we will do when we go to the FPGA. I will club that part in the case of with the FPGA because there is a reason to do that. We will see that when we learn how to take the skew of the clock in the analysis, we will see that. Okay. But a proper designer takes care of the clock period, take care of the skew, take care of the whole time violation again with the skew and all that. So everything is done properly. So you have a data path, register, combination circuit, register, we say okay the clock period should accommodate the TCQ, TCOM and the setup. Done, the clock period is chosen, and if there is a skew that is taken care. Similarly to avoid the hold time violation here we have to make sure that the minimum delay of this flip flop plus the minimum combination delay should be greater than the minimum hold time. So that is also taken care. Similarly with the FSM you have the logic here decoding the next state and output from the present state, and we again here make sure that the clock period is met. T clock is TCO plus T comp T logic plus the T setup time, and the whole time again TCQ, T logic, T comp minimum should be greater than the T hold minimum. This is all taken care. So what is, why are we worried about metastability? Okay. So the question is that we take care of in a data path, in an FSM we take care of the destination register setup time and the hold time. Okay, so why, like that is an essential part of the design, the timing design. Then why do we worry about the metastability in flip flop? Because it is only violated then the metastability happens. So that is a question. We take care of the setup time and hold time violation in register to register path in sequential circuit and data path, and when can metastability happens in data path. Okay, so that is the question. So look at this picture, then you might get a like, or look at this picture where things can go wrong. Like we have analyzed this path, from something clock comes, the output change, it propagates through here and it comes here. Nothing can happen because we have taken care the clock period is greater than this path delay. So where things can go wrong, that is, so we will let us put this picture of the data path of the sequential circuit. Now look at where things can go wrong, and I am also showing some input here directly coming to this combination circuit. Now you know that we have some input to this register, we have some input to the combination circuit, and we are not sure where it is coming, this is coming from. Similarly the state machine has inputs, external inputs. Maybe some inputs are coming from the data path, some inputs are coming from some other place. So now the crux of the problem is these, these inputs we are not sure where it is coming from. It is okay if all the inputs are coming from a register clocked by the same clock, but assume your data path has 2 clocks and this is the clock and there is another clock 2, and there is a register which is clocked by the clock 2, that output is coming here, then that has no phase relation with this clock, and this data propagating through the combination circuit may not meet the setup time here. Okay. So there could be a problem of metastability here. Okay. Similarly these inputs we do not know where it is coming from, maybe it is not from the same clock, or it is coming from a process which is not related to this clock. Say example is that something is moving and there is a limit switch, it touches a switch and that switch output is coming saying that the limit is reached here. So that probably that movement is driven by a motor which has got nothing to do with this clock. So that process has no relation to the phase of the clock here, so it can violate the setup time at this input. So whenever there are inputs which is not synchronous to the clock, you are clocking the registers, they can cause metastability in the respective register. So this input can cause metastability here, this can cause metastability in this particular input flip flop. Okay. Now look at the state machine once again, this the state flip flop to the state flip flop path absolutely no problem. We have taken care of the clock period, hold time, this Q and so on. But you see there are inputs from maybe from the data path which is clocked by the same clock, but maybe one of the input is coming from elsewhere which has no phase relation to this clock, then that can cause metastability in this flip flop because it propagates through. It does not matter because it is coming randomly, this logic will not do any good, like if it is quite random with the clock, this logic delay I mean doesn't, it makes no difference, okay, because the whole pattern is shifted by a constant delay. As far as the kind of the probabilities are concerned, it does not upset the probability of a setup hold time violation, because a constant delay will not do any good. So these inputs which are not synchronous to the clock are the culprits of metastability in a sequential circuit. So, and we call that as asynchronous inputs. Okay. So asynchronous inputs in a data path like this or like this, or in a sequential machine, sequential finite state machine, the asynchronous input can cause metastability in the flip flop. Okay. Now the name, like the solution is in the name itself. The metastability happens because the input is not synchronous, input is asynchronous. So if somebody asks you what is the solution, like even if you have no clue, you can say yeah, asynchronous input is causing the metastability, so synchronize it. Okay. Like if it is synchronous it does not happen, you can boldly say synchronize even if you do not know how to synchronize. So this is one of that type of question. To answer it is very easy, but you may not know how to do it. Okay. But maybe in an interview you can kind of impress people, maybe that question can give you a good job, say like why metastability happens in sequential circuit, you say asynchronous input, what is the solution, you say synchronous, synchronize it, then you get the job, you get a good salary. So we will see how to kind of synchronize it. So when I want to bring clarity to that, asynchronous input to a sequential circuit can cause metastability in flip flop. When we say asynchronous input, it's an output from flip flops working on a different clock reaching the destination. It is output generated by some process not synchronized to the sequential circuit clock. As I said, maybe something is moving which is touching a switch, that movement has got no relation with the clock which we are clocking the input register. So those are asynchronous input. How to solve the problem? As I said, synchronize the input to the sequential circuit clock. Okay. That means that you have to, there are edges which is changing randomly, the input is changing anytime, but now we have to make it change with respect to the clock of our system clock. Like we have a sequential circuit or a data path, now we have to make sure that this input which was kind of no phase relation to the clock we are clocking the data path or sequential circuit, we have to make sure that this input change in phase, okay, with a constant phase relation to this clock. Okay. So that is simple, because suppose assume this was a kind of scenario, this input was coming from outside going through the combination circuit to the some flip flop in a sequential circuit. Now this was asynchronous. Okay. Now how to synchronize it? What we do is that we put a D flip flop, put that asynchronous input, connect that to the D of the flip flop, and the Q you take it and give it to this particular combination circuit. So this is the target sequential circuit or data path. This is the synchronizer, we call it a single stage synchronizer because there is only one flip flop. Okay. Now if you look at the clock waveform, a clock comes and whatever is the analog input here, if it is like this, then it appears here with a delay of TCO every time, anything like even if it changes before, upon the clock edge only it changes the state, and you know that now it has become synchronous because every time after the clock it appears neatly with a delay. Now we are sure that when the next clock edge comes here, it is setting up properly because much before that the data is set up here. Now you have the time for it to propagate through the combination circuit and meet the setup time. Okay. So that is how it is synchronized. It is same now, like you have a TCQ plus TCOM plus T setup, that should be less than the clock period. Okay. So we have kind of synchronized, we made sure that irrespective of the input change here, the output is synchronized to the clock edge. So just a flip flop That is all what we need to synchronize, okay. But fine, I mean that sound great, the really great. Once again a clever student will ask a question, is the problem solved? Now we said that this is changing with no relation to the clock, and that comes here and upset the destination flip flop, causing metastability here. But now we have the same issue here. We have put a flip flop and said fine, now the data appears with a delay and it is the setup time is met here. But what about this flip flop, okay. Now the data at the input of this flip flop has no relation to the clock here. So now this can get into metastability. So we have not kind of solved the problem, right. Looks like this is a kind of cheating, you shifted the problem, okay. So we didn't solve the problem, we shifted the problem. The question to ask is again, is that a good thing to shift the problem at the outset? At least that's the problem with the pictures, I have drawn a picture at the kind of a raw impression is that we have not kind of improved upon the situation. But it is not so, because in a, like you see, there is a thick line here and there is a very thin line here, okay. That should give you a clue. In a sequential circuit there could be 20 flip flops, and an asynchronous input reaching the 20 flip flops can put all the 20 into metastability, okay. But now we are catching that analog input in a single place, okay. Now earlier it might propagate through different combinational delay. We know that when you say a COM here, we have multiple paths. If there are 20 flip flops here, there are 20 different paths, and depending on the delay we are sure that maybe at least few of the flip flops can get into metastability, because the path delay could be different. But now that means this input is sampled at different time by different flip flop. So with the random behavior of this input we are sure that 1 or 2 can get into metastability, say, I mean I am say under the quotes, because we have to really see the probabilities, which we have no time to analyze in this class. But I suppose you get the picture, but then the situation is improved because we are put a single flip flop and sampling it, it is tightly controlled, there is no path delay, it is directly coming here, and if at all a flip flop get into metastability is this flip flop, not all these, okay. Now the only hope we have is that instead of all the flip flops getting into metastability, we have a single flip flop might get into metastability, and we are hoping that before the next clock edge it comes out of metastability, okay. That's the best hope we can have in a single stage synchronizer, that it may happen that this solve the problem, it may happen that this get into metastability, but if it gets into metastability it comes, the output comes out of metastability with a proper margin, so that it can propagate through the combination circuit and meet the setup time for the next clock edge, okay. So we assume that definitely the analog input cannot be a very narrow pulse, it has to be at least 1 clock period duration, so that even if it misses one it is caught in the next, okay. So naturally, and we know that because we have put a flip flop here, it has to be there for at least 1 clock period, then only it can propagate through that. So there is a latency, the use of synchronizer will add a latency, so it will be detected by the sequential circuit only after a clock, and that also necessitate that the input pulse width should be more than 1 clock period wide, for to be able to properly propagate here. So this is how the synchronization is done. We have not completely solved the problem, but we will look at it, as I said, we have isolated the problem to a single flip flop, a single place sampling is done. Earlier the sampling was done at multiple places at multiple instants of time because of the variation in the path delay. Now it is done in one place, okay. So if it is solved, it is solved for everything. If it is not solved, it is not solved for all other flip flops. So it's better than the earlier case. Earlier we had no control, like some might get into metastability, some may not, but here it is tightly controlled. So let us come to that. So that is what is listed here, okay. Now the final analysis is that the synchronizing flip flop can get into metastability, but the problem is isolated to synchronizing the flip flop. But we are assuming that before the next clock edge it comes out of the metastability, and we also assume that the input remains valid for one more clock cycle to be correctly sampled and captured by the synchronizing flip flop in next clock. So now the good news, so this is a single stage synchronizer, this is a synchronizer, this is a sequential circuit. The good news is that the probability of a flip flop remaining in metastability decreases exponentially with time, okay. Now mind you, read carefully, the probability of a flip flop remaining in metastability decreases exponentially with time. That means that if this analog input asynchronous input violates the setup time or hold time, and if this get into metastability, as the time passes the chances of it coming out of the metastability, it is a chance, it is a probability, is higher and higher. As you give 1 nanosecond extra, the chances are more. You give it more time, you have more chances of it coming out of the metastability. It is probabilistic. We cannot say deterministically 100% of the time it will come out, but we increase the probability, okay. So the metastability we can only handle probabilistically. So what we do is that we will reduce the probability of or we will increase the probability to such an extent that in the lifetime of the system we are building, this happens very rarely, that is a basic idea behind it, okay. So what is the time available for the flip flop to resolve? That time is called metastability resolution time. That is the time, metastability resolution time is the time available for this output to resolve, come out of metastability, okay. So now if you look at it, you have a full clock period available, T clock, but you know that once the output get into metastability, it should come such that the setup time is met here by the next clock edge. So if you have a clock period, it has to be resolved T clock minus T setup minus T combination delay. Then only if it is resolved it will be correctly set up here. So for a single stage synchronizer, the metastability resolution time, that is the time kind of available for the output to resolve to a valid state, is nothing but, that is called TR, the metastability resolution time is T clock minus T comp minus T setup. So that is clear, okay. Now say that this has to be ready T setup plus T comp which is subtracted from the clock period, that is it. Now it will be good if we can increase this, okay. So suppose we the situation is like this, we found that there is an asynchronous input, we try to synchronize it, we put a flip flop and we do some analysis, we find the TR and find the probability. There is a analytical expression for doing it, we can model that and get an expression. Then we find that the probability is not very is kind of not very low, that is remaining in metastability. Then we have to increase the TR so that to make that probability very low, that's a game. So we suppose we calculated this, we found the probability and we find that it is still high, there is a high probability that will remain, then we have to kind of increase it. Now one way of increasing is that to reduce the clock period, but that is that is not on, because we have when you design a circuit we have a clock target, okay, depending on the performance we need. Like we are doing some computation and we have a requirement of a throughput, so many operations per second, and we know the data path architecture, how many clock cycle it takes for the computation of the result we are looking for. Then we fix the clock period and we go back and design to meet this clock period requirement. So we cannot arbitrarily kind of reduce the clock period. So our aim is supposed to increase the TR, because we find the probability is still high, so we want to reduce it. So what to do next? The like T clock cannot be reduced, okay, T clock cannot be increased, that will affect the performance. So the next question is that, and the setup time, all this depends on the technology you are working with. Suppose you are working with 22 nanometer technology, the setup time is fixed for a flip flop, nothing can be done about it, okay. So we may not be able to do anything with this. So the question is that, can we reduce this combination delay, okay, say 0, can we make it 0, okay. So go back and look at the single stage synchronizer, we are asking whether we can make it 0. So no magic, we cannot do any magic. The problem is that this flip flop output is going through the combination circuit and reaching here. So to make it 0, what we do is that we block it, okay. That means we put another flip flop here, okay. That means this flip flop output is going to yet another flip flop input. Advantage is that there is no combination circuit in between. So as far as that path is concerned, the combination circuit is not there. So that is called a double stage synchronizer, okay. So that's what we do, a double stage synchronizer. Our aim is to reduce the probability of, once it get into metastability, decrease the probability that it remaining in metastability. So we give more time. So now you see that there is a clock period here between these two, and this has to resolve setup time before the clock period. So the resolution time, metastability resolution time of the first flip flop in a double stage synchronizer is now increased. It is the T clock minus T setup. Earlier it was only one stage, it was T clock minus T com minus setup, okay. Now we have reduced it and nothing comes free. We know that an input changes, it will take 2 clock cycle to propagate it here. So there is a latency after the input changes, after 2 clock period only the input will reach the sequential circuit. So that's a price we pay, we have a latency of 2 clock period, okay. Now suppose you find the TR, now it is better than the earlier, you find the probability, you find, oh no, it is still kind of probability is quite high, you want to still reduce. So we have to increase TR further, okay. Now we are already at the tether end, we have only 2 terms, one is T clock and T setup. The game is to reduce T setup, as I said this is fixed and we cannot do anything, and now we are forced to increase the clock period. But if you increase the clock period, the performance of this sequential circuit will suffer, we don't want to do it. So now the next question then to ask is that, let us not reduce the frequency of this clock, but let us reduce the frequency of this clock, okay. So what we do is that we will put a clock divider, like assume that the clock is coming from this side, we put a clock divider, say divide by 2 or divide by 3 or 4 like that, and then give it a log clock to the synchronizer, but the sequential circuit will work with the original clock. So that is how that if we increase T clock, system throughput will be affected. So let us keep the system clock as same and we reduce the clock frequency by dividing the system clock, and that is called multiple cycle synchronizer because it takes multiple clock cycle to synchronize. Okay, that's why it is called multiple cycle. Earlier it is double stage, there will be 2 clock cycle to synchronize. Here it is multiple clock cycle to synchronize. So that is the game here in a multiple cycle synchronizer, wherein you have the clock of the system, could be sequential circuit or a data path, which is divided by a counter. Mind you, when I say mod n counter, n is not a huge number like say 20 or 64 or 128. This mod n is like 2, 3, 4 like that. It is not a big counter. We cannot have such a kind of large discrepancy between the synchronizer and the system clock. So now you see the TR is now, because this was a clock period, when you divide by mod n, the clock period is increased by n. Okay, so you divide by 2, the clock is divided by 2, so the clock period will be 2 times T clock. So in a mod n counter the clock period is n into T clock. So the TR is nothing but n into T clock minus setup time. So now we have like improved the TR by order of, like if it is 2 times, if it is 3 times or 4 times and things like that. So we have really improved, and this should be sufficient. Like if you find the probability of a double stage synchronizer is that offer is not good enough, if you give it 2 times or 3 times it will improve, because we are talking about exponential. Okay, we say the probability of that remaining in metastability decreases exponentially with time. So if you give twice it goes exponential, and the advantage you get is exponential. So normally this should be sufficient. Okay, so and now you know that the latency is 2 clock period but the clock period itself is n into T clock, so it is 2 n T clock. There is a lot of latency here, like something happens, it takes, if suppose n is say 3, it takes 6 clock cycle to reach here, which you have to see whether it is kind of tolerable for the system you are working with. Okay, so it is a multiple cycle synchronizer which reduces the probability of this particular flip flop remaining in metastability for long, like this remaining in metastability. Okay, so n is 2 or 3, and there is many times people, instead of doing like this using a counter, because at the end of it, like when you say, suppose you say there is a mode 3 counter or mode 4 counter, it is 2 flip flop. Okay, so use 2 flip flop for synchronizing and 2 flip flop for counter. Some people okay, now there is another issue here which we have not kind of addressed. You see there is a, because of this mod n counter, there is a skew between this clock and this clock. Okay, now you see that this clock is coming with a delay of this counter. Okay, so and this clock comes early. So the like if you analyze this path to this path, the available time is not T clock minus T skew. So like there is this skew affects very badly because it eats into the time available, because now it is not that T clock is greater than TCQ plus TCOM plus T setup. It is T clock minus Q should be greater than this particular path delay. So normally what is done is that, since that to avoid that combinational, the large path with the skew happening, a D skew flip flop is put, so that the problem comes here. That means you say T clock minus T skew should be greater than TCQ plus T setup to kind of not to affect the large delay path. So a D skew flip flop is added here in the multiple cycle synchronizer. So I think we are coming to the end of the lecture. So what we have looked at is the problem of metastability in flip flop that stem from the an issue in the cross coupled latch which is used in the edge triggered flip flop. So we have to meet setup and hold time, and I said clearly explain in some odd detail that it comes from the master latch, the setup time with some clocks clock path inverter delay. You have to subtract it, then that delay of the clock path will add to the hold time, then the slave latch delay is the propagation delay, and we say that for a successful operation it has to be met. If it is not met, three things can happen. The output can be valid, so it can be 0 or 1, we are not sure. It can be it can take long time to resolve it, it can get stuck in between, and this happens particularly in a sequential circuit or a data path with asynchronous input, because all register to register path we do the proper analysis for clock period and the hold time violation, so nothing can happen go wrong, but the asynchronous input can create trouble because it is not synchronous with the clock, it can change any time. And asynchronous means any input which is not having a phase relationship to the clock we are using for the sequential circuit. The solution is to use a synchronizer that can be achieved by a single flip flop, but if that can get into metastability, that is better than many flip flops getting into metastability, and our hope is that it comes out of metastability by the next clock edge. And we also see that the more time it has for to resolve, more the probability of its coming out of the metastability. So idea is to give more time for it to resolve. So we have seen the metastability resolution time for a single stage flip flop, it is T clock minus T com minus T setup. To remove T com we put 2 stages of synchronizer, then it becomes T clock minus T setup time, and if that is not enough we reduce the clock of the synchronizer by dividing it, then we have N T clock minus setup as the resolution time, the latency is 2N T clock, and this counter can add skew in the path, the clock path, that can affect the total clock period available. So sometime we add a D-skew flip flop. So that is about the synchronization. So I have addressed the issue, I have already given a solution. So what is remaining is maybe little more detail, one more solution, and something specific to the state machine when the input is asynchronous, and something about the reset, then we can wind it up. I am hoping that in the next lecture halfway through we can wind it up. So this is an important topic. I was doubting whether I will be able to cover that in the course, but then not to talk about is kind of it's not good after learning so much about how to design and all that. So I think it's an important topic, please go back read it, and if you want additional material you can kind of look at the textbooks if it is available, or look at some papers, the white papers which is available in the with the manufacturers, so that this can be learned well. So I wish you all the best and thank you.